Good day, viewers. In this video tutorial, I'm going to teach you in less than 5 minutes flow rates of a fluid in a pipe or hose. Flow rate of a fluid in a pipe or hose. Let us look at the question. They said, water flows along a horizontal pipe of cross-section area 48 cm square, which has a constriction of cross-section area 12 cm square. Then here, at one place, if the speed of the water at the constriction is 4 meters per second, full stop, calculate the speed in the wider section. Let us go to what? Solution. But before I go into this solution, if you have not subscribed to this channel, endeavor to subscribe to enable me grow my channel. You are just helping me by subscription. Your subscription helps me to grow my channel. Then subscribe, share, comment, and turn on the notification bell, so at any time I post a new video, you will receive those video. Thank you. Now let's go to solution straight. I have this solution. I go to solution without wasting time. I have a pipe. Let us say this is a pipe, and this pipe is a uniform pipe. It has an end, and this is a pipe. I have this area at this point, I call it A1, and the velocity of the fluid at this point, I call it V1, and the area at this point, I call it A2, and the velocity at this point, or the velocity of the fluid at this point, I call it V2. This is the velocity, and this is a straight line, which is a uniform 2. Then mass per seconds of fluid. I'm taking a fluid as my reference point. The mass per seconds of fluid passing through this area is giving us mass 1, change in time. That's what we call mass per seconds. Gushing out through this point, that's passing through this point, is equals to density of the fluid, cross-sectional area of the tube, velocity of the fluid. Cross-sectional area of that particular tube times the velocity at that point. Then, talking about the mass gushing out. The mass gushing out here, I call it mass 2 per seconds. That's the mass per second. Gushing out through this place is equals to density of the fluid, I call it density 2. Then cross-sectional area, I call it cross-sectional area 2. And the velocity in which the fluid is used to gush out, I call it V2. Then here, making M1 subject to formula, that cross multiplication. Making M1 subject to formula, I have M1 is equals to density 1, cross-sectional area 1, and velocity 1, and the change in time. That's change in time. Here, making the mass subject to formula, I have mass 2 is equals to density 2, cross-sectional area 2, velocity 2, and change in time. Then here, looking at it, the mass passing through this place is the same as the mass coming out from this place, because this tube is a uniform tube. So the mass of water coming out, going through this place, is same thing of the mass of water coming out from this place, I can now say that mass 1 is equals to mass 2, because mass passing through this place is equals to the mass coming out from this place. Since this mass 1 is equals to mass 2, this man is equals to this. It's implied that this is equals to this. I can now say that this 1, A1, V1, change in time is equals to density of 2, cross-sectional area 2, velocity at 2, and change in time. Then now, this man and these are the same. It will cancel itself. I will now have this to be what? Density 1, cross-sectional area 1, velocity what 1 is equals to what? Density 2, cross-sectional area 2, and velocity what? 2. And this is what we call flow rates. Flow what? Flow what? Rates. Flow rates. Or we call it volume flows. Volume what? Flows. Flow rate of volume flows of what? A fluid. In this case, when we say fluid, it comprises both gas, both liquid, both water, anything. As far as it passes through the pipe, we call it fluid. But we have two types of fluid. We have what we call compressive fluid and incompressive fluid. When we talk about compressive fluid, we talk about gas. Gas is a compressive what? Fluid. Gas is a compressive fluid. It's an example of compressive fluid. So if we are talking about compressive fluid, we say gas. That means that what? Density 1 is not equals to what? Density what? 2. For what? Compressible what? Fluid. For what? Compressible fluid. Therefore, this formula is used for what? Compressible what? Fluid. Then, when we talk about incompressible fluid, we said this is equals to what? Density what? 2 for what? Incompressible. Are you following? Incompressible what? Fluid. Means that what? This is equals to this. For what? Incompressible what? Fluid. So if this man is equals to this, that means this formula, this one, area 1, and V1 equals to what? Density 2, area 2, and velocity 2. This will cancel this. Since this man is equals to this will cancel this. I will have V1, and A1, V1 is equals to what? A2, V2. And this formula is formula we use for what? Flow rate. This is a flow rate for what? Incompressible what? Fluid. Flow rate formula for what? Incompressible what? Fluid. Why this one is a what? Flow rate formula for what? Compressible what? Fluid. When the fluid is compressible, this and this are not the same. But when the fluid is incompressible, which example of incompressible fluid is water. Look at the formula we use for the fluid called what? Incompressible. Example what? Water. We say water. This is what we use for that. Then when we talk about what? Gas. This is what we use for what? Gas. So you have seen the what we call flow rate. This formula is called what? Flow rates. Are you getting what I'm saying? So this is the formula we're going to use to solve this what? Equation now. We're going to use this formula to solve this question. So when I apply this formula, you will not be what? Confused. Then let us use this formula for the equation. Making the use of the formula for flow rates for incompressible fluid. The formula, we said A1 V1 is equals to what? A2 we said what? A2 V2. Where this one is cross-sectional area at what? Wider pipe. Why this one is a cross-sectional area at constriction. This one is a cross-sectional area at wider pipe. Look at it. I write this. Look at it. This pipe now. Look at this pipe. Look at this pipe. Look at this pipe. Can we view the pipe now? Look at this pipe. This is what? Area 1 V1, and this is what? Area 2 V2. Are you getting what I'm saying now? So this is the cross-sectional area of the bigger place, wider place. Why this one? Cross-sectional area of what? Constriction. They said, looking at the question, water flow along a horizontal pipe. Look at the horizontal pipe of cross-section area 48 cm squared. Cross-sectional area which is 48 cm cube, which is for this man, which has a constriction. Look at the constriction. Look at the constriction here. Look at the constriction, which has a constriction of cross-section area 12 cm. Are you getting what I'm saying now? Which has a constriction of cross-section area 12 cm squared at one place. If the speed of the water at the constriction is 4 cm, calculate the speed in the wide section. Look at the wide section. Look at the constriction section. So now, we've now said A1, which is cross-section area at the wide place, which they said is equals to what? 48 cm squared. Then looking at this is in cm squared. Looking at the velocity they give me, the velocity is what? Meter per second. Why this man is in cm? Are you getting what I'm saying? Velocity is meter per second. Why this man is in cm squared? So we are going to change this man to meter so that we will have a uniform unit. In physics, we will make use of what? Uniform unit, not a what? A mixed unit. Since this man is a meter per second, we are going to change this man to meter. So changing this to meter, I will now say 48 divided by 100 is how we change centimeter to meter. That's how we change centimeter to meter. But right now, the centimeter we are changing to meter is squared. Therefore, we are going to square this 100. Are you following me? How do we change centimeter to meter? We change centimeter to meter by dividing that centimeter by what? 100. But right now, the centimeter we are changing to what? Meter is a what? Square. Therefore, we are going to square the 100 we are dividing. Therefore, we are going to have 48 all over 10,000, and this will give me 0.0048, which is 1, 2, 3, 4. Then now, that gives me meter squared. That's meter squared now. And I come to what? V1, which is what? The velocity at what? Wider section. That velocity at wider section is question mark, the one they said I should find. I will now go to what? VA2. A2 is given to me as what? Come over here. A2, which is cross-section area 12 cm at what? Constriction. That has a constriction of cross-section area 12 cm square. So at this constriction, the cross-section area is 12 cm square. I have to change it to meter. I will say 12 divided by 100. But the centimeter I'm changing to meter is squared. I have to square it. And I have 12 all over 10,000. And that will give me 0.0012 meter squared. Then now, I will come over here to talk about V2, which is the velocity at the constriction part. The velocity at constriction part is given to me already as what? 4 meter per second square. Look at it here. If the speed of the water at the constriction is 4 meter per second, is already giving me the speed at what? Constriction, but what they are asking me the speed at the wider area. Then using the formula now, A1 V1 is equals to A2 V2. In this case, A1 is given to me as 0.0048 times V1, which I'm looking for, and equals to A2 is given to me as 0.0012 times the velocity, which they said 4. Then now, doing this now, I will now have to what? That what? V is equals to what? 0. V is equals to what? 0.0012 times what? 4 all over 0.0048, and this will give me V is equals to what? 1 meter per what? Seconds. That means that my V is equals to 1 meter per what? Seconds. And that's my what? Answer. How did I get 1 meter per second? If you times this will give me what? 4. This will give me 8. This will give me 0. This and 0. Which is the same thing as this. It will give me what? 1 meter per second. That's the velocity what? 2. That's the velocity 2 I'm looking for. And velocity 1, I need to say at 1. Velocity 1. Then looking at it, this is my velocity 1. Then what do you discover now? You say that at constriction, the velocity is high. That's why if you go to where they are what we call car wash, if they want to rinse the car they have already washed, they will press the pipe, the hose, they will reduce the area of the hose. The water will be gushing with a higher what? Velocity. You will see the water gushing out with higher velocity and spray on that vehicle, and they use it to rinse the vehicle. After they have washed with soap or detergent, they will now press the mouth of the hose, and it will use it to rinse it. But immediately they remove their hand and the hose become wide, what will happen? You will see the speed of the water, the speed which the water used to gush out will be reduced. So this is what happened. So when you reduce the cross-sectional area of the pipe, the velocity will be increased, while the cross-sectional area will be reduced. Then if this man is increased, if you increase the cross-sectional area, what will happen to the velocity? Velocity will reduce. You have seen it now that when we increase the cross-sectional area, the velocity will reduce. Then when we reduce the cross-sectional area, the velocity will increase. That's what we discover here. See that V1 is smaller than V2. Look at the V2. The V2 is given to me at 4 meters per second. Then look at V1. And the V1 has a higher cross-sectional area, while V2 has a lower cross-sectional area. Look at V2 cross-sectional area. This. So thank you for giving me time on this, and thank you for subscribing. Thank you for sharing to your friend. Thank you for commenting. See you in the next video.